Okay, so I will start. I don't know how we'll go with time, so I will try to be fast. So my colleagues always joke on me that I put the time wrong, but I hopefully it's good today. So last time my title was catchy because it was called About Time, and well, this time I went for something not so catchy. But I still hope it will be fun. So, okay, my name is Krzysztof Dryś. I work at Ingrid. I hope most of you know me. And I will be mostly be coding today, a little of presentation just to have some slides to begin with. So I will be talking about benchmarking. I will be writing benchmark. That will be the core of my talk. If you don't know table tests, it will be a nice occasion to learn about it. If you don't know much about benchmarking in Go, hopefully you will learn something. And I will talk about how you can, mostly it's about caching. So it's a global cache, different patterns, different approach to global cache. Data synchronization patterns might be a bit misleading because it will be like one way of synchronization in global cache. So how can you do a global cache in your application? I mean, the best way you can do it, if you can, is a static structure. So on the start, you initialize the static structure, static map, or something like this. You pass it all to your Go routines, and it's fast, it's simple to understand. The only problem is that sometimes it's not possible. Most of the time, it's not possible. So then you can use mutex, and mutex has this one advantage which probably everyone who graduated from computer science knows a thing or two about mutex. And in Go, a simple Go mutex usage is simple to understand. So if you do start a function, you write log, then you do defer, unlock, and then you do simple operation. It's simple to understand, and you will hopefully have no deadlocks. And also, once you have a log, we can do more stuff than just update one map. You can, for example, update two maps. You can have a one cache which is by one key, another cache which is by another key. You can do lots of stuff. But mutex will allow only one concurrent read, obviously, and it's tempting to do a lot of stuff inside mutex. And I've seen complex applications which were very hard to understand because of mutexes. And I mean, if once you are locked on the mutex, once you obtain mutex, it's attempting to do more stuff than just read from map. And if you call a function, you can be in trouble. Like it can lead to very complicated code. And if you are worried about log contention, you can use read-write mutex. Just to ensure we're on the same page, read-write mutex allows concurrent reads and only one write. So it tries to avoid the load contention. Simple usage is, again, simpler to understand. You use log when you write, you use error log when you read. But then if you do anything more complex, it becomes much more complex, and it can still lead to write content or log contention writes. And as we will see, it's not that efficient. I don't remember which version exactly, but sync map was added. It's, again, simple to understand because it's just like normal map it's not typed, so because we don't have generics in Go, sorry. And it's in the standard library, so everyone can use standard library, and so it's a good idea. And there's a typo here, but apart from this, it sometimes avoid log contention, but even the official documentation says it's not always. And it's suited for two very specific use cases. One is when your cache grows only, so when you don't update keys, and the other is when the different Go routines are updating different keys. So again, this is I think a bit tricky because it says sync map, so you would think it's always for you, but in practice it's maybe, oh, it even says here, you need to read the documentation to understand that maybe most of the time you are better off using mutex. And there is mapping atomic wrapped in atomic value. I will talk more about this. This is one of my favorite patterns. This gives you very fast reads and very slow updates. And this is actually a foundation for syncmap. Syncmap is a more complex version of this. I won't go into details right now. I will show you the code how to put map into atomic value later. And you can use channels because channels are cool, and then when you read documentation about Go or tutorials about Go, you always read about channels, read that channels are great, read that channels are super fast. So why don't we use messages inside channels to have reads and writes? I mean, in theory, you could put more requests than just one read. You could put more complicated logic, and because channels are more or less simple to understand, this will be simple to understand, but it will turn out that it's quite slow. And there's a summary which is not there yet. Okay, so I will try now to do some code, and to do it I will just delete all the code which is here and try to write it from scratch. Let's see how it will go. Yes, of course. Yes, I can.
Good pattern that you only delete tests.
Yeah. Otherwise, how can I know? It would be green, red. Okay. So what I will be doing, I will be benchmarking map. So this will be. I will be both storing and I mean map will be int to int, but I don't want ints everywhere because to feel it a bit more generic, I will have a type alias for key and for value, but it will be ints anywhere. I will use maps of size of 100,000. Okay, and I will be implementing this interface, which is, I mean, you know, just the simple store, get, and set. And I will be, this will be for my table tests. Okay, so I will first write a simple first one. So this be map store. Okay, and let's see how fast I can type it. So map key value. Okay, now I will implement the store interface. Yes, I can.
Go to the presentation.
I wonder if this was recorded. How do I do it? Presentation mode. Okay, I wonder if this will work. Okay, so I will do get like this, and it's v okay, and not possible because I will be writing. I will be doing concurrent updates, and it's not possible to do concurrent updates on not sync map. And you are so smart. How do I create a new file?
Go to Flash.
Sorry? Thank you. New file maybe. Okay, so it will be mutex store. Nah.
Don't ask.
Mutex store struct. So I will be using. I will have this again. No braces, but sync mutex. Okay, and implement interface store. Yep. Okay, so as I was saying, the pattern, if you are not doing anything complex, is quite simple. You just always need to make sure it goes like this, and you do like this, okay, and then you return. Okay, cool, and now it's okay, and okay is P. I don't feel comfortable in this mode, to be honest. So exit presentation. Not so good. Yep. Okay. I'll do like this. Okay. So now I have two stars. So yeah, I have some tests. I will maybe to be faster. I will not writing. I will just comment this. I have so much commented code. Okay. It goes deeper and deeper. Okay, so what's happening here? This was a good question. Okay, so what I want to do is I want to do tests, but I need to initialize my maps, my stores somehow. So I will write an init function. So I will write make map store, which I will be initializing each and every star with a pre-filled data. So what I will do now is can't see. Yes, sorry. Hopefully I will get better at this soon. Okay, so I will copy this into a new map. Okay, and I will return map store with like this, and I will initialize mutex store same way, make mutex store. Okay, and it goes like this. Okay, so I have now two stores. I will go to writing some tests. So here you can see it, but now you do. It's like magic. So I will initialize a map which will be my initial data. So I have a key space size of 100,000, and I will use put every second value from this map to my map, and I will do something like this. Test case. I will have sorry. One is map, and the store is make map store. Okay, and the other one will be mutex. So it's make mutex store. Okay, I promise it will be a little faster once I write the test first. Once I write the first test. Okay, benchmark synchronous. It's the hardest part, right? Testing B. Okay, so cases, test cases, and for test in cases, range. I will do a new test. It's B, right? So I will run a subtest. V testing V. So I will do new random reader, and I will set it to 0 just to have all tests to operate on the same data. And now I will do standard benchmark test. Okay, test store read now get. It's get. Okay, I will put key into a new variable, so it's runs. No, it's error. Sorry, int, and it's size. So I take one key from the key space, and I will put it into the thing because I'm always afraid that compiler will optimize my code away and it will be gone. And hopefully this will work. No, totally not. Go test. Oh. And I'm so scared, but okay, sort of works. Okay, some applause would cheer me up, to be honest. Thank you. So, I mean, if you see, I mean, the one thing which you don't see, oh my, and I don't know if there is a way to fix it.
Command plus.
Command plus. Ah, yes. Okay, that's one thing which I need to work on my next presentation. Okay, so if you remember my previous presentation, I mean, the interesting fact here is that the cost of obtaining a mutex is 30 nanoseconds. Totally not needed in your work, but might be a nice fact to impress your friends.
Could you check a variation of the code when you are not using defer statement? Because I heard it's not that fast, but I'm actually interested if this is true or if this is just a
yeah.
It should be improved in the next version.
Let's see it. Oh, nice. That was interesting. Okay, so this will get interesting over time. Okay.
and it's supposed to be optimized in the version to come. So.
Yeah. Okay. I was not aware of this, and this, to be honest, it's.
Probably if you will use this from the many concurrent.
Yeah. I mean, of course, I'm very thankful for this comment, despite it ruins for my presentation. But okay, I'll try to live with this and move on. I mean, so okay, what I was hoping to show you was that how much time it takes to obtain mutex. It is some time, but not as much as I thought. So, I mean, whole housekeeping takes more time. Okay, so maybe.
Let's go back to different.
Yeah, no. Okay, it's let's see. Maybe I'll just okay. Let's see how it does in asynchronous situation. So what I will do is this run parallel funds pb. Okay. What it will do, it will with this code, it will spawn as many processes. I mean, it will spawn as many Go routines as there are processors available. So to see it, so I don't know. Go max pro. Okay, this is this. So right now it will spawn to. Yes, sorry. I mean, maybe not sorry, but P4 PB, not terribly sorry. Okay. It will spawn 2 Go routines. Okay, so one interesting fact here is how to read this. I mean, it spawned 2 Go. I've given it 2 processors to process the data. So it spawned 2 Go routines, And as you see, I mean, the number of items for normal maps which are processed doubled, which is, I mean, quite obvious because we are not interfering with each other. But as you can see, the number of items which were processed per second per normal mutex actually went down because of the cost there is to obtain mutex. And we can give it more, when we can do more about it, because we can do something like this. I will call it massive because it will be a lot of GoWroutines, or because it will be massive failure. Let's see which will be true. Set parallelism to 1000. So right now it will spawn 1000 GoWroutines per one available processor, which will sum up to 2000 processors. And hopefully this makes sense to you. So as you see, the number of map reads per second did not change. I mean, we have many GoWroutines, but still only two system threads available. So this number, I mean, is slightly smaller, but probably this is because there is larger number of GoWroutines, so Go runtime needs to put some effort to scheduling them. But the mutex is doing much worse. I mean, adding more concurrency to mutex is making it sad. Okay, so unless someone has another nice comment to cheer me up, I will now do read-write mutex. And I know you can't see it, but it will get better. Okay, so I need now to change some code. Yep. So you probably noticed that I'm not using updates at this moment, but I plan to use them shortly. Yes, yes, and yes, and yes, thank you. So I have, where am I? Okay, right here. Okay, so one thing which is nice about table tests is that now I need to only write it here, and I will get even more data out of this. So what's interesting here is that RW mutex, it's I mean, in theory, the cost of obtaining it once is the same as for normal mutex, but in concurrent setting is not as fast. I mean, in theory, obtaining we are only reading data, so obtaining log should not be broken, but it's still not as fast as reading from a normal map. So it shows you that it's not as efficient as you could hope. So how much time do I have, Tobiasz? 5 more minutes.
Yes.
Expecting more? No, okay. Well, I don't expect anything from you at this stage, but okay. So now I will do updates. Update key. Now I do value, and now it goes like this. Set. Why does okay? Yep. And I need to pass it to massive as well. Okay, so I'll run the test one more time. Okay, I hope that all of you caught the pattern of the table test at this moment. So you separate the test cases from the actual running the code, and using the subtests in a loop, this makes its code look quite nice. Well, hopefully you agree with this. Okay, so let's see. I mean, this can be disregarded because nothing happens in here. There's just skip, and it's quite interesting to see what's the footprint of an empty call. So you can see what's the cost of mutex. And one interesting thing to see here is that read-write mutex are not free. I mean, it's still some kind of trade-off between read and writes, because when you do our only writes, read-write mutex is slower for writes than the normal mutex, and I mean, it gets even worse with the more Go routines which you have. Okay, and maybe I will go now to the last pattern. I mean, I had more, but it's always like this. Okay, atomic. No, I totally didn't want to copy this code. This one, okay. This one. Atomic. Okay. Atomic store, and it's the value will be inside atomic value, and so it's like this. Okay, let's put it like this. I will rename the receiver, and it's IS. I load the value and I coerce it to map. Maybe not the pretest code, but it must do for now. So what it does, the atomic value, I'm not sure if anyone is experienced with this. If not, I really encourage you to check it. It uses compare and swap, yes, instructions from the compiler. It's simple but very efficient for some use cases. But how do we update? So the updating is a bit more complicated, because what we will do, we will make a copy of the map. I need to now set the original key value, and now I will store it to atomic value. Okay, and now I only need to make atomic store. Yes, so how do I do it? Yes, store map, and it's atomic store. Okay, and I will just add new test case. Okay. So what? Maybe as we get the data, I will give us more time to understand what's happening here. So there is atomic value, which is just a reference to any interface, and it's not type again, sorry, but when you load from it, you get sort of the freshest value, and when you set to it, I mean, you can't set to this M because it can't be read at the same time by different threads or coroutines, sorry. So you just copy whole contents of it and you update the copy and you store the copy. And to ensure that it's all safe, you put it inside mutex, and hopefully I have the results here. Yes, I have. Okay, so what's interesting here is that okay, it works. Is that read is the same? I mean, it's the same speed as map, even under concurrency. So atomic is here, and it does not suffer from any issues. But if you look at update is terrible because it needs to copy the whole map. So we need to adjust it to your use case. So I will be finishing now. So I didn't go through channel. I will just say that channel has a terrible performance. I mean, it's slowest of all of the three kinds. I mean, it's not as slow as update of atomic, but it's very slow otherwise. So, I mean, what was surprising for me is that mutex is not as bad as it might seem, especially if you have a friend who will tell you not to defer, and if you I don't care that much about the performance, and if you don't care that much, if you use it in a simple way. And read-write mutex is not that much gain, which was a surprise to me. But first of all, you need to understand your use case first. So for example, for us, in our cases, which we have at Ingrid, we have caches which are growing slowly. So updates are rare and reads are very often. So in such cases, atomic value is a very good use case. Despite, I mean, what it says is about updates. And it's always nice to think about mixed approaches. So for example, you can use channel only for synchronizing writes, and use atomic value for reads. Yeah, that's all. Thank you. Do you have any questions? No, okay. Thank you.